Hi, welcome to our 23rd lecture of our graduate combinatorics course. Today we'll continue talking about bipartite graphs. As you recall from last time, we define a graph to be bipartite if there is a partition of its vertex set into two independent sets. So more precisely, we have this, you can think of it in terms of this picture, you have, say, two sets, or you can partition the vertex set of the graph into two parts, such that there are no edges inside each part. So there are no edges with two vertices both in X, and there are no edges with both the endpoints of that edge in Y. So the only edges that you could find are edges going between with one endpoint in X and the other one in Y. So something of this form. Okay. So from this definition, we deduce that if we have a bipartite graph and we start at a vertex, and we do a closed walk, so we walk on edges and come back to the vertex where we started, then the number of edges that we have used must be even, because every time we use an edge of the graph, we change, we go either from X to Y or from Y to X. So in order for us to return, we must have used an even number of edges. And this is a necessary condition for the existence of a bipartite graph, and it's also sufficient. And that's the result that we stated last time and we started proving. This is a result due to the Hungarian mathematician Konig. And it states that if we have, we study here for connected graphs, I'll mention after the proof that the same result is true for if we disregard connected. But let's assume connected for now, and we say that the graph, the result is that the graph is bipartite if and only if the graph has no odd cycles. And we did the direct implication from gamma bipartite implies it has no odd cycle, using the argument that I just described earlier, that the only closed walks in the graph must have even length, and therefore the only cycles that you have must be even, and therefore you have no odd cycles. And now we started last time, but we didn't quite finish it, the proof of the converse. So we assume now that gamma has no odd cycle, gamma is connected, and we want to prove that, that gamma is bipartite. And to do that, we pick a vertex in the graph, let's call it A, and for any vertex B in the graph, which could be A as well, we define L of B as the shortest length of a path from A to B. So with this definition, L of A is 0 because we don't have to go use any edge to go from A to A. So this is the only vertex that has L0 here. And now the neighbors of A, the vertices here, will have L equals 1. And then the neighbors of the neighbors, which are the ones here, these 5 vertices in my picture, have L equals 2, and so on. These ones are going to be L equals 3, and so on, L equals 4. Okay. And now, what do we want to prove? We want to prove that the graph is bipartite. So we want to find a partition of its vertex set into two independent sets. And so we define X to consist of all the vertices with L of B being even. So X consists of the vertex A, the vertices which are 2 steps away from A, and the vertices which are 4 steps away from A, and so on. Okay. And we define Y by the vertices which are at a distance, odd distance from A. So this will consist of the neighbors of A, and the vertices that are at distance 3 from A, and so on. Okay, so our goal is to prove, so I'll move on to the next page. So our claim is that X and Y are independent sets that partition the vertex at V. Okay. One part of this statement, it's easy to prove, the fact that they partition V. because the graph being connected, so gamma being connected, implies that for any vertex, let's say x of v, L of x is well defined. There is a path. So this means there is a shortest path, AX path. So that means that L of x must be, it's either even, which means x belongs to the set x, or L of x is odd, which means that x belongs to y. So this implies that V is a subset of x union y, but both x and y are subsets of vertices. So that tells me that V equals x union y. And it's also obvious that x intersect y is empty set because a number cannot be both even and odd at the same time. Okay. Now, the only thing left to prove is that each of x and y are both of them are independent sets. So I'll just do it for x, and the proof for y is similar. So now here I will prove that x is an independent set. Okay. So to do that, I will do a proof by contradiction. So assume that there are, let's say, b1, which is not equal to b2 in x, such that b1 and b2 are adjacent. So here's a picture schematically. So we have A. Somehow we go to b1. So in our case, let's say, is an even number of steps. I have this edge between b1 and b2. Yeah, this is the edge that I want to show that it actually doesn't exist, but for now I assume that it exists. And then I can have another, it could be maybe another way to go from b2 to A. Okay. So what we're going to do, so we have, so because L of b1 is even, there is a path, there is an A b1 path, let's call it p1, of length L b1, which is, I guess, of length L b1, okay, which is even. All right, so this is kind of my path here, p1, the one going from A and ending up in this picture, b1 in 4 steps. And similarly, we have, similarly, because we have LB2 is also even, there is a path, and I will write it this way. There is a B2A path, B2 of length LB2. And P2, for me, starts at B2, goes all the way up and ends up at A. And now, let me squeeze it here. So what I want to say is that we consider the following walk. So we start at it's P1. So it starts at A, and it goes all the way to P1. So it starts at A and it ends up at B1. So these are the P1 path. Then we use the edge B1, B2. So B1, B2 here. This is an edge by our assumption. So it's a legit walk so far. And then we do the path P2. So now we go from B2 all the way back to A. And this is the path P2. Okay. And what do you notice? This walk starts at A and ends up at A. So this is a closed walk. So let's call this walk W. So this walk is a closed walk. And what about its length? Well, we're using LB1 steps for the first part. So I have LB1 steps here. This edge uses 1 step, and the path P2 uses LB2 steps. And so in total, I'm using LB1 plus LB2 plus 1, even plus odd. This is going to be an odd walk. So what I have here, this walk W is a closed odd walk. Okay, so it's something like the one that I draw in my picture here. Let me maybe use a different color. So it's kind of like you go at A, go down like this, go here, go back here, go back here, go back here, and go back here. So it's in this picture, the walk is of length 9. And what do you see? This walk has an odd cycle in it. It's this little cycle of length 5. So that's what the contradiction will appear from, is that because every odd cycle, we'll prove in a second, every closed odd walk must contain an odd cycle. Okay, so let's write this up. So define W to be the walk consisting of the path P1 followed by the edge B1, B2, and then by the path B2. The walk W is closed because it starts and ends at A, and its length is LB1 plus 1 plus LB2, which is odd. So now what I need to do is prove the following lemma. In any graph, any closed odd walk contains an odd cycle. And I'll add here, we can talk about it a bit later, but be careful that this is not true if you replace odd by even. And that's actually easy to see because you can do a walk between two vertices in which you can start at the vertex A, and let's say here you have maybe not good. Let's say U and V. You start at U, you go at V, you go back at U, and you can continue like that. So you can find the U walk of even length using only the edge UV. So there's this U walk of even length that just goes back and starts at U and goes back at just uses the edge UV and goes back to U, and you can do as many steps as you want, 2, 4, 6, 8, and so on, even. But this walk obviously doesn't contain any even cycle. Okay, so now what's the deal with odd? Okay, so how do we prove this lemma? So this is proof of the lemma. And you see that if we prove the lemma, then we are done with the theorem, because we will have this closed odd walk W, and by the lemma, it would have an odd cycle, but that contradicts our hypothesis. So to do that, we use a strong induction on the length of the walk. So let's just say the length of the walk is the number of edges. So I need to give this walk, let me close the walk, W prime, just to, okay, W prime. Okay, so if the length W prime is 1, then W prime is a loop, which is an odd cycle length 1. So then W is an odd cycle, so we're done. Maybe if you want to restrict yourself to simple graphs, you can skip maybe this case, but say if we're a simple graph, then we say if the length of W is 3, then yeah, if you're in a simple graph, then W must be of this form. You start at the vertex U, you go to vertex V, then you go to a vertex lowercase w, and you come back to U. So in this case, W is a cycle of length 3, and we are done. You cannot do this with just 2 vertices. Okay. And now for the induction step, assume that the length of W prime is odd and at least 5. Okay, so what is W prime? Okay, we start at some vertex, let's say U0, you go U1, blah, 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 UK minus 1, UK. So here we have used UK minus 1, UK. And UK equals U0, okay? So that's our walk, and K, which is the length here, because you have U0, U1, so on, UK minus 2, UK minus 1, UK minus 1 back to U0, that's the length. K is the length of W prime is odd, and it's at least 5, okay? Now, we have this W prime, and we have 2 cases. So in case 1, it's kind of our lucky case, U0, U1, all the way up to UK minus 1 are distinct. So meaning they're pairwise, so, you know, none 2 of them are equal. And
here's what I found.
Oops, sorry. Okay, and case 2 is when we are going to have some repeat in them. There exists. So I'm going to put it like this: U0, U1, blah, UK minus 1, not distinct. Okay, so in the first case, it's easy because if U0, U1, UK minus 1 are distinct, that means that W prime is actually a cycle. And because it's actually a cycle, and it actually is an odd cycle, so then we're done. Now, if U0, U1, UK minus 1 are not distinct, we can rearrange the vertices, let's say in this walk, so that, let's say U0 is the first vertex that repeats. Okay, so we can, without loss of generality, we can think of our walk as starting at U0, going back somehow, going on a walk W1 and coming back to U0, and then starting back again at U0 and doing another walk W2 and ending up at U0. So without loss of generality, U0 is a vertex that repeats. If that's not the case, then you can shift the walk and you can have it start at such vertex. Now, what can you tell about the length? So the length, in this case, the length of W prime will equal the length of W1 plus the length of W2. But the length of W prime is odd, so this number is odd. So that means that either W1 is odd or W2 is odd. If W1 is odd, then W1 is a closed W1 is a closed walk because it starts at U0 and ends up at U0, and it's odd of a length which is strictly less than W prime. So then by the induction hypothesis, W1 has an odd cycle. And similarly, and because W1 has an odd cycle, then W prime has to have an odd cycle. And something similar happens on the other side. If W2 is odd, then it's an odd closed walk of a length which is strictly less than the length of W prime. And by the induction hypothesis, it must contain an odd cycle. And therefore, W prime must contain an odd cycle. So that finishes the proof. And so with that proof in mind, so this does proves the lemma. And this lemma basically finishes the proof of our theorem, because like I said, you have this W, and by the lemma, W contains an odd cycle, but we don't have any odd cycles. Our hypothesis was that we have no odd cycles. Okay, so this also the proof for to do that Y is an independent set. I leave it as an exercise, so you should do it. It's essentially almost the same Y independent set. I leave it as an exercise. And this proof actually gives you an algorithm to figure out if a graph is bipartite or not. So if a connected graph is bipartite, you pick a vertex and you do this traversal of the graph, which we'll talk about it in a few lectures when we learn about trees and so on. And this is what is called a breadth-first search. It's kind of like let's say a less adventurous way to traverse the graph, in the sense that you start with the vertex A, then you just visit all its neighbors. So that's the vertices with L equals 1. Then you visit all the neighbors of the neighbors. These are the vertices with L equals 2, and so on. So this is one way of traversing the graph. And it can be used to figure out if the graph is bipartite, because you get this partition into vertices at even distance from A and vertices at odd distance from A. And if you look inside X and you see an edge, then the graph is not going to be a bipartite, because any edge inside X will correspond to a closed odd cycle, a closed odd walk, which would correspond to an odd cycle. And similarly, any edge inside Y will give you a closed odd walk, and that will lead to an odd cycle. But if you find no edges inside X and no edges inside Y, then the graph is bipartite and you're done. Now, I mentioned before about connectivity hypothesis. That's not actually needed. And so before I deal with that, let me give you some simple definitions. So in a graph gamma, we can define, so in the graph gamma, one can define the following relation, X, symbol to use here. Let me use this X equivalent to Y, if and only if X, there exists a path from X to Y, or path or walk, it doesn't matter. So this relation is a binary relation, but it's actually an equivalence relation on the vertex set, because X is equivalent to X, because there is a path, it's just a vertex X. If X is equivalent to Y, then Y is equivalent to X. That's also easy, you just reverse the path, and I leave it as an exercise, so it may be easier to change this definition to there is a walk. It makes it easier to prove transitivity, because in transitivity you have a walk from X to Y, then you have a walk from Y to Z. If you just concatenate these two walks, you get a walk from X to Z, and you're done. So this is an equivalence relation. Again, I leave you as an exercise to figure out the details. And what it does, any equivalence relation, it partitions, we get a partition of V into equivalence classes. And these equivalence classes have a name. These are called the components of gamma, or sometimes are called connected components of gamma. So let me give you an example. If I have this graph, okay, I have this graph, I have vertices 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is a graph, okay, vertex set are these numbers from 1 to 16. And what are the components of this graph? Well, 1, 2, 3, 4 are in one component because you can get between each of them by a path or a walk. Then another component will be 5 and 6. Then we have 1, 8, 9, 10. And then 7 is by itself, its own component. This way. And then 11 is by itself. And then this one, 12, 13, 14, 15, 16. That's another component. So here you have 6 components, okay? So the definition that we've given for a graph is connected if and only if. So this is our definition. A graph is connected, means that for any X and Y, any X and Y in V, there exists a XY path. Now this definition is actually, you can see from the definition that the gamma is connected if and only if gamma has one component. Okay. Now, coming back to our problems about bipartite graph, if the graph is so if gamma is a graph, not necessarily connected, so we can, it's the same is true. Gamma is bipartite if and only if gamma has no odd cycles. And how is that true? Well, the first part is easy because if gamma is bipartite, it doesn't matter how many components it has, then it's obvious that it's in each component you cannot have any odd cycles. So that does it. And the other way around, if gamma has no odd cycles, then, so if you think about this implication, then gamma, let me draw a picture. Maybe gamma has different components. Okay, maybe these are the components of gamma, but each of them is a bipartite graph. So each component, so if gamma has no odd cycles, what you can prove is that each of its components has no odd cycles. That's obvious. And that implies that each component is bipartite. And then each component is going to have this partition into a blue and a gold. And so you can do a blue here and a gold. It's not unique because you can match them, you know, like I can do something here. I put this is the gold and this is the blue. And now you take the union of this, you take this, the union of these blues, and you put them into one component. And you take the union of this gold, and you put them into this component. And all the edges, because you're basically taking the blue bipartite sets are independent sets, and when you take the union of them, you cannot create any edges. So they're not going to be, there are not going to be any edges inside the blue part. So all the edges can go between them, and that implies that gamma is bipartite. Okay. Now, one more thing before we go, for bipartite graphs, if you have this partition, so gamma bipartite with, let's say, partite sets X and Y, it makes it easier to figure out the edges, the number of edges. So if this is X and this is Y, and you have edges just like this, only in between them, then if I sum up the degrees, so the result that I want to say is that the number of edges, so cardinality of the number of edges, equals the summation over all x in x of degree of x, and it's the same thing as the summation over all y in y of degree of y. And how do you do that? Well, you can prove this by counting. If, let's say for x, for example, count order pairs xe, where x is in x, e is an edge, and x is contained in E. And the key thing here is that for any edge, E, one of its endpoints is going to be in X. Yeah, and the other one obviously in Y. And so if you do this count, this double count, you can get this result. Okay. So we talked about connected. Let me give you one more definition about graphs. So let's say we have a gamma, the vertex V and E, a graph. Now, we have various notions of subgraphs, okay? So what is a subgraph of gamma? So this is a graph. What do we call a subgraph of gamma? Well, a subgraph of gamma is a graph that's obtained from gamma by deleting some vertices and some edges. So this is a graph, let's say gamma prime, V prime, E prime. So with the property that V prime is a subset of V, E prime is a subset of E, okay? And the endpoints of any edge in gamma prime are the same as its endpoints in gamma. So you just delete, so subgraph, you just delete vertices and edges. So let me give you an example. Let's say gamma is this graph. 1, 2, 3, 4, 5. Then gamma prime this is a subgraph. So basically, this is a subgraph because I deleted vertex 1 from gamma. So I deleted the vertex 1, and then I deleted the edges 2, 3, and 3, 4, and I ended up with this graph. Okay, so this is a subgraph of gamma. Okay, now the following, let me give you something that is not a subgraph. If I do this is not a subgraph gamma because this edge 3, 5 is not in gamma, but it is in gamma prime. So this is gamma W prime. Okay, so that's subgraph. Now there are various kinds of subgraph. A subgraph is called spanning. So a spanning subgraph is a subgraph gamma prime, v prime, and e prime as above, but with additionally v prime is the whole vertex at v. So for spanning subgraph, you get it from this one you just delete some or possibly none edges of gamma, and that's how you get a spanning subgraph. So gamma prime is not spanning, gamma W prime is not spanning, but let me give you, let's make a picture in here. Two, three, like this graph, 1, 2, 3, 4, 5, gamma triple prime, this is a spanning subgraph because I kept all the vertices and I only have two edges, 2, 3, and 3, 4. So I deleted the other ones. Okay. And one more notion, which is induced subgraph. So this is again a subgraph, gamma prime, e prime. But the property that it's obtained just by deleting vertices. Delete some, again, possibly none vertices. So the so here basically E prime, the edges, this consists of all edges of E intersect with the vertex set of pairs V prime 2. So basically, if you look at the subset of vertices V prime of this graph, when it's induced, every edge that was between two vertices on V, between two vertices of V prime in the graph gamma must stay inside the graph gamma prime. So let me see where I can give you an example. So for example, if I look at 1, 2, 3, this is not induced because this edge 1, 3 is not in it, is not an induced subgraph of this one. But if I look at this one, this is induced subgraph because among these vertices 1, 3, so what this is 3, 1, 3, 1, 3, 4, 5. In the graph gamma on the top, there is the edge 1, 3 still here. There's the edge 3, 4 still here. There's the edge 4, 5. So this graph, as you can see, has been obtained from the one on the top just by removing the vertex 2, and that's what you get. So that's what the inducement. Okay, now, so these are just some names that we'll use throughout the remaining of the course. So like I said, spanning, you keep all the vertices, but you may be deleting some edges. Induced subgraph, you delete some vertices from the graph and you keep all the edges that are among the remaining vertices. Okay. All right, so now let's move on to our new topic. So we are going to talk about trees. So trees are a special kind of graph. So say gamma. So this is, we'll talk about simple graphs. So there will be no loops, no multiple edges. Gamma is a tree if gamma is connected and acyclic. So acyclic has no cycles. Okay. So some examples. So let's look for n equals 1 vertex, just a single vertex, that's a tree. N equals 2, 2 vertices adjacent by an edge, that's a tree. Now, I will do here a picture, a split picture between what I called unlabeled, and let's put it here, and labeled trees. So unlabeled, we don't put a, so here I put the vertex on 1. Over there, I just delete any name that I give the vertex. Unlabeled, there's this on n equals 2, there's one edge. Labeled, right? Labeled with vertex with numbers 1 and 2. So I'll just label them with numbers from 1 to n. Okay. So far nothing too, you know, you may wonder why in the world we do that. We'll see in a second. Okay, let's see what happens when n equals 3. So when n equals 3, we have 3 vertices, and the graph has to be connected, but there are no cycles. So this is the only, I mean, it can appear in different drawings. You know, it can be drawn like this, but it's essentially the same, or okay, any other way. There's just one. Now, what happens when we draw the label tree? So labeled, I can label them 1, 2, 3, but I can also label them, I can put 1 in the middle, this is 2, 1, and 3, or I can label them as I can put 3 in the middle, I can put 1, 3, and 2. Now these purple trees are considered different when you talk about label because their edge sets are different. So you see the one on the top, the edge set consists of 1, 2, and 2, 3. The middle one has edge set 2, 1, which I can write as 1, 2, and 1, 3, so it's different from the other one. And bottom one is 1, 3, and 2, 3. Okay, so that's when I consider them to be different. So that's the difference between labeled and unlabeled. So labeled, you see, you get more trees, and unlabeled, you get fewer. Let's go to the next one, n equals 4. We won't have room here, but so if we think about unlabeled trees, you can do this one, this path, or you can also do a vertex adjacent to all the others. You can try to think to find others, but yeah, see how many there are unlabeled. And label, I'm not going to draw them here, but I can tell you that there will be 16 labeled trees. So we'll get to that in maybe not this lecture, but in the next lecture. And so what happens as you move along? Well, there's no formula. There's no nice formula for the number of unlabeled trees on n vertices, but for the labeled ones, There's a theorem due to Cayley and also proved by Borchardt before Cayley. So I think Borchardt proved it 1860 and Cayley 1889, something like that. And it says that the number of labeled trees on n vertices is n to the power n minus 2. So these numbers here, this number here was 2 to the power 2 minus 0, 2 minus 2, sorry, which is 2 to the 0, which is 1. This number here is 3 to the power 3 minus 2, which is 3. And this number 16 comes from being 4 to the 4 minus 2. Which is 16. So we will prove this in the next lecture. But before we do that, so let's discuss some properties of trees. So let's draw some more trees. Let's see, n equals 5. We have a path, 5 vertices. You can have one of these stars. And here actually there's one more. You can have something like this. So these, I think these are the only ones when n equals 5. And yeah, you can draw all kinds of trees. Just make sure everything is connected. You can draw them kind of this weird shape like I draw here, or you can draw them kind of more organized fashion this way, similar to the ones in the bipartite graph theorem. Okay. Now, what do we notice about all these pictures? So, well, you have one that if you put labels on them, well, if you count the number of vertices, here you have n equals 5. And how many edges do you see? All of them, each of them have 4 edges. And it's the same thing for all the others. So each of them will have the number of edges will be 1 less than the number of vertices. And the other thing that you notice is that each of these trees contain vertices, at least 2 vertices of degree 1. So let's prove that. So let's start with some easy things. Proposition that gamma tree with n vertices. So 1, if n is greater or equal to 2, then gamma contains at least 2 leaves. What are leaves? A leaf is a vertex of degree 1. Okay, and 2, the number of edges of gamma is n minus 1. Okay, so how do we prove this? So the proof for 1 is similar to what we did before. So remember in one of the previous lectures, we showed that if a graph has minimum degree 2, then it contains a cycle. And in that proof, the way we did it, we took a maximum path and we show that that's how you get the cycle. So we'll do something similar here. So consider let P, let's give it a name, P, x0, x1, blah, 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 xk, b, path. You can take it of maximum length. If you want to be in more generality, you can take it to be maximal, which means it cannot be extended by any other vertex. So I'll give you an example in a second. So it'll be a path of maximum length. So you have this path. So all these vertices are distinct. Now, what can you say about xk? Well, if xk has another neighbor this way, let's say xk plus 1, then that makes a longer path, so this cannot happen. And if xk, then if xk has a neighbor back on this path, then we get a cycle. We get a cycle here, so that cannot happen. So therefore, the degree of xk must be 1, and the degree of x0 also, the main point, must be 1. So these are the leaves. So x0, xk are leaves. Now, like I said, here's an example of a tree. I have here 1, 2, 3, 4, 5, 6. So here, 1, 2, 4, 5, 6, this is a path of maximum length that cannot be extended. But 1, 2, 3 is also, it's a maximal path. So the 1, 2, 3 is a path that cannot be extended, but it doesn't have maximum length. You can see. Okay, and now quickly, I'm a bit out of time. So for the second part, you use induction on n. So n equals 2. This is the only graph. Well, you can do n equals 1. This is the only tree. So it has n minus 1 equals 0. Here, n minus 1 equals 1. And then let's say if you want to do pk implies pk plus 1, the induction step, really quickly, you take a tree T with k plus 1 vertices. K plus 1 is greater or equal to 2. You have a leaf here. Let's call it x. Let's call this remaining tree T prime. So what you do is T from which you remove x, the vertex x, this is T prime. Now T prime has k vertices. T prime has no cycles because it's obtained from T, which didn't have cycles, by deleting something. And there's one thing that you have to argue is that T prime is connected. So you have to argue that if you give me any 2 points here, A and B, inside T prime, there is a way to get to them. Now, why is that? Well, every vertex because T was connected, there is a path from A to B inside T. And every vertex inside that path must have degree 2. But the vertex x has degree 1. So it means that x is not on that path. So when we delete x, that doesn't affect this path, AB, it still survives. So this is connected. So T prime is a tree, and therefore it has k vertices. A tree T prime must have k minus 1 edges. But, well, how many edges will T have? Well, we deleted a leaf, a vertex x of degree 1, so T must have k minus 1 plus 1, which is k. All right, so I'll stop here, and next time we'll talk more about trees and proof of codes and Cayley's theorem.